Between about 360 and 370 million years ago, the area that is now Ithaca, New York, was underneath a shallow sea. It was at low latitudes, between 10 and 20 degrees south of the equator.
What is now the east of where we're standing, there was a huge mountain range that was formed by the collision of what is now Europe with what is now North America. Those continents came together about 400 million years ago and formed this mountain range that began to erode sediment. That sediment is what we see behind us here.
When these continents came together, they pushed up a series of mountains that today we call the Appalachians. But 370 million years ago, this mountain range was in the middle of a much larger continent, which eventually would become what geologists call Pangaea.
We don't know exactly how big they were, but they may have been as big as the modern Himalayas. In any case, that mountain range extending from what is today Scandinavia to what is today Alabama was eroding and shedding sediment down into a shallow sea.
Just as today the Ganges River drains off of the Himalayas into the Bay of Bengal, forming a large delta, the sediment eroding off that ancient Appalachians also formed a large delta, which geologists call the Catskill Delta. What is now central New York, where Ithaca is located, was the offshore part of this delta, covered with seawater.
We know that this part of that big delta was covered by seawater because we find marine fossils, seashells in the rocks right here. Because these fossils look like animals that live in the ocean today, we think that these fossils represent animals that also lived in an ocean. And so we infer that there was ocean here over what today is dry land.
These shells look a little bit like clams with two shells, but if we examine them a little more carefully, we discover that they're not exactly like modern clams. They look more like another group of modern animals, which most people are less familiar with, called brachiopods.
Brachiopods were the most abundant and diverse group of fossils here in the Devonian of central New York.
Brachiopods live in today's oceans, but they usually live in out-of-the-way places, like caves or under ledges.
We compare these fossil shells to living shells, and we conclude that these fossils represent extinct species.
The rocks here in the walls of Cascadilla Gorge in Ithaca are arranged in layers, suggesting that they formed during a time when environmental conditions were changing. When you think about it, layers of anything must represent change. These rocks are made of sediments, tiny grains of rock and mineral. The shape, size, and arrangement of these sediment grains contain clues about the conditions under which they were deposited.
Geologists can use those characteristics to reconstruct the history of their accumulation.
You can see this if you pour some sediment into standing water today. The larger or heavier particles will settle to the bottom first, and the lighter or smaller particles will settle later. That's telling us that different conditions are suitable for deposition for different kinds of grains. That tells us that when we see different kinds of layers in rocks, like those in Cascadilla Gorge, we're seeing a change in conditions. This inference that layers in sedimentary rocks tell us about changing conditions in the ancient past is a key insight of geology. It means that conditions were such that a layer was deposited, then something changed, and a new set of conditions was established that led to deposition of the overlying layer. Then something changed again, and so forth. This way of thinking also implies that between these changing conditions, some time passed. And this is another key insight in geology. It says that the planar surfaces between layers represent the passage of time during which conditions changed. And this is the source of a statement that geologists make often, but is sometimes puzzling to non-geologists. A geologist will look at a set of layers and say, I think some time is missing right here. What we mean when we say that is that there must be some period of time represented by the planar contact between two layers of sediment. A surface where there is missing time is called an unconformity, and it's one of the most important ideas in geology. Now, when we zoom in more closely on some of these layers, we can really investigate in detail what's going on. Such a study is like a detective story. We look at the clues left behind. We're the crime scene investigators trying to reconstruct events that we did not actually witness. First, the sequence of events. Sediments accumulate because of gravity. And so we can assume that in an undisturbed stack of layers, the oldest layer is on the bottom and the youngest is on the top. This principle is called superposition, and it's one of the key principles for telling stories in geology. It allows geologists to infer the chronological arrangement of events that resulted in the deposition of a set of layers.
If we find this in a rock like this one, what does this tell us? It tells us that just like in our experiment with the sediment in the water, all the grains forming this rock must have been deposited all at once. The heavier ones settled before the lighter ones. Geologists use that as an indicator of rapid deposition, such as might occur in a storm or an underwater landslide. So that by looking at the grains in this rock, we can reconstruct something about the conditions under which it was deposited, such as the turbulence of the water. Larger grains settle in more turbulent water. Finer grains settle in calmer water. So it could be that when you stand back and look at a series of layers like this, we're looking at an alternation of conditions, changing conditions through time. Some sediments are deposited quickly, and some sediments are deposited gradually. Every rock has a history, a series of events that took place to form that rock. But geologists weren't there when the rock formed. So how can we possibly know the conditions under which that rock formed? Well, we do it by comparing the characteristics of the rock, the size and shape and composition of the grains in this sedimentary rock, to grains that are moving in modern water. And we look at both of those and we compare them, and we come up with a series of hypotheses that says this is the conditions under which this rock formed. We weren't there to witness it, but we infer it from evidence. It's like a crime scene investigation. So we can reconstruct the conditions under which this rock formed, and we can use that reconstruction to reconstruct the history of a place, Cascadilla Gorge in Ithaca, New York. If we do that for places all over the world, we can reconstruct the geological history of the planet.